discussion. Does anybody have any first questions that I'll get out of the way?
Yeah, I'm not answering them.
So, how close would we have to be to another galaxy that was had a big blazar coming out pointing at us for it to affect us?
Ooh. So the jets get pretty big. They get to sort of thousands of parsecs, which is basically thousands of light years. Maybe millions, really big. But there's no galaxy close enough to us. I think that would happen. Certainly not any that's likely to have energy. The nearest one is Andromeda. I can never remember the numbers. They're not. Fortunately enough, they're not close enough. I think it's really it's something I want to look into more though. Is just for fun. Is exactly how far away one would have to be for it to do something to us.
Do they sort of wobble around like laser light shows?
No, they're pretty focused in the direction they're going. What you see, so you can actually see it on this one. They're pretty focused, and then they hit. They basically pile into gas, and then you get these woofly bits on the end of a jet. But the main bit is quite focused.
Was it gyroscopic sort of action?
I don't think so. I don't know, to be honest. Yeah.
There's gamma ray bursts. There's some completely different process from what we were describing.
Yeah, gamma ray bursts. As far as I know, they're more to do with supernovae and they're sort of star scales rather than galaxy scales. I mean, you get black holes and you get the stellar black holes as well that form from a supernova explosion when a star dies, and you do find that they have jets as well. You sort of find jets at all scales.
Could you clarify the difference between the inactive and the active galaxies?
Yeah, so the active galaxies are basically the ones that have this accretion disk of stuff going around the center, going around the supermassive black hole. So a black hole, a galaxy with a supermassive black hole that is actively eating up stuff, basically, where there's a lot of stuff falling into it, is an active galaxy. And then you have all that stuff that you saw in the cartoon. Most galaxies, like the Milky Way, just don't have anything really near the black hole, although we did think for a while that there was a cloud of gas going towards the Milky Way's black hole that would fall in, and then there'd be a lot of X-rays, but it now looks like it's not going to quite go past it.
So they still have the black hole?
They still have the black hole, yeah. Every galaxy...
Black hole, but
yeah.
there's nothing close to
There's nothing around it, yeah. Yeah, it's sort of eating everything up. They cleared it away. Really animated with hands.
So it's been doing that process to begin with, and then it stopped, as if.
So we don't really know at what point in a galaxy's lifetime this happens, and it's possible that a galaxy could be active and then become inactive and then active again. Not quite sure when it happens and what triggers it, what starts it off. There's a lot of things about them that we don't know. I don't know, it's probably going to be the theme of this part. But we'll try. Yeah?
So, what's causing the jets to shoot out all of that material, and why is it on those 2 points and not in every other?
Yeah, good question. Again, something that's being looked into. So it seems like the magnetic fields get twisted on the poles. And it's sort of, it's at right angles to the rest of the system, so it's probably due to the rotation of that. Somehow is twisting up the magnetic fields, and then you've got the electrons that are spiraling around it. Again, that's an area that people are looking into, and I don't think there's a sort of consensus on how they actually start.
So is that part of the accretion disk that's being fired out?
Yeah, I think it's bits sort of coming off the accretion disk that are getting fired up.
So does the occurrence of these blazars mean that it's theoretically possible to escape a black hole?
No, it's sort of it's outside of the event horizon. Unfortunately not. Yeah.
With all the unknowns, is it because telescopes aren't big enough to look at it, or is it just because it's really complicated? Like, are you limited by what you can actually see?
You are limited by what you can see, yeah. So what you really want to be doing is getting right down, looking at the jets really close to the black hole, and we don't have the resolution to do that. We do have it's called very long baseline interferometry. So you need radio telescopes that sort of spread the entire of America. So there's one in America that goes right across the country. There's one that goes right across Europe, and you sort of need the telescopes on that on that size to start probing these the jets at sort of those scales. And we've got a few radio telescopes that are being built. There's one called the Square Kilometre Array, which is going to be partly in southern Africa and partly in Australia, and that's going to hopefully be able to figure it out. I mean, the other thing is it's complicated physics, and you need a lot of computing power to run your simulations to try and see if what you come up with an idea and try and run your simulations, see if you can form these jets in your computer. And the computing power as well, I think, is that's not my side of things, but that's takes up a lot of computing power to do that.
Is there like a defined shape of a black hole?
I mean, a black hole is a theoretical explanation. I mean, it's a black hole itself is an infinite point.
Sure.
What we talk about is when you define sort of like the size of a black hole, you define its event horizon, which will be a sphere around it, which is the point at which.
Can it be determined by the magnetic forces at all, or by the
What?
anything else that is observable surrounding? Like, does it have an entrance point? An exit point?
No.
Like, is it just?
It's pretty much, yeah.
Zero?
But you find but I mean, as I say, you get the disk going around it rather than everything. Rather than the stuff falling into it all directions, you do get this disk sort of accreting around it. Disks form sort of in all parts of the universe to do with angular momentum of stuff going around. It's the same as how the planets formed around the sun. You get all the planets in the same plane because they all formed out of this disk of stuff that accreted around the.
Do you know why that is?
It's to do with angular momentum. And there's some physics that I could probably dig out of my brain.
That's a very good question. Now look it
Yeah.
up and come back and let us know the answer.
So you're going front, yeah.
Gravity.
Gravity.
So you've got something like the Andromeda Galaxy and our galaxy.
Yeah.
And they're getting attracted together.
Yeah.
Now, they're thousands of light years apart, aren't they?
Yep.
So is the sort of gravitational tow from the Andromeda Galaxy from where it is now, or where it was thousands of years ago?
That's a good question. I mean, that's a good question. That I've never really thought about before. Does gravity have a time? Don't know. I have to think about that one. I know what I mean. It's the same as thinking that we're seeing Andromeda now, but we're actually like the light we're seeing is actually Andromeda.
Yeah. But
Thousands of
presumably
years ago.
Andromeda's not where we see it now. It's somewhere else
Yes.
now.
Yes. But then at some point now becomes irrelevant. At some point, when you're talking about galaxies and talking about stuff in space, that are thousands of millions of light years away, now becomes a bit pointless because it really is just depends on your frame of reference.
Do you make adjustments?
Pardon?
Do you make adjustments?
Yeah. So all the
Like based on the distance of like if one galaxy is closer, another one's further away.
Yeah, so whenever you're talking about like sort of the brightness of objects, you correct it for the distance. So when we talk about how bright objects are in the optical, you have their apparent magnitude, which is how bright they appear to be, and then the absolute magnitude, which is if all these objects were at the same distance, how bright would they be compared to each other? If someone had a hand back up.
Yeah, what you sort of labelled as obscurations of ellipsoid sort of shape, is that just normal ionisation and fluorescence sort of processes going on? It's so bright that it just stops you viewing everything.
So it was the obscuring torus, which we think of as a sort of donut shape of dust that's surrounding the system. That the dust just stops you from seeing through to whatever's behind it. That is very much a generalisation, and certainly that cartoon is from sort of 20 years ago. We call it the torus because it's a nice thing it's an easy way to think about it, but I don't think there is genuinely a donut shape of dust around. We don't really know what that is that's stopping us from seeing in there, and that's that's something that I'm pretty sure some people were discussing last week at a meeting that we don't actually know.
It's just physically blocking.
It's just physically blocking.
Rather than so much illumination coming off.
No, it's not you being overwhelmed by light. It's not saturation. Yeah. Yeah. Sorry.
Got too many things though.
Oh, good.
Still started worrying about when now is and isn't.
Yes.
And then I started thinking about if a jet aeroplane goes by, when you hear it, it's not where it is it?
Yeah, that's right. Yeah.
So we've got this all power. But do we, if a jet aeroplane went by faster than the speed of sound, then it could have hit us before we heard it?
Yes.
So we rely here on the fact that nothing can travel faster than the speed of light, or else it will hit us before we heard it.
Yeah, I mean, as far as we know, the speed of light is a speed limit that can't be broken. You know, there's nothing can travel faster than the speed of light. That's just one of the laws of physics.
But you did say earlier some things that appear.
They appear to be.
Is that the doctrine?
It's similar to that. Yeah, it's because it's so tightly sort of collimated coming towards us that by the time the light it will have moved by the time the light it moves as the light is coming towards us. Ooh, so maybe.
It won't hit us before we see it.
Ooh. But let's go with there's nothing that's going to hit us, so we don't need to worry about it.
That's not what you were saying a wee while ago.
There is an excellent book called Death from the Skies by the bad astronomer Phil Plait, which documents the many ways that the universe is trying to kill us, and has a small section on active galaxies trying to kill us if anyone's interested in that. Sorry, asteroids will kill us first.
Another question.
Yeah, sure.
Because I feel really, really happy that we're not going to be destroyed by Andromeda. But I've got another one.
Yep.
And that is, could somebody build one of their little one of these on Earth and point it at me?
Well, it's basically a version of the Large Hadron Collider in space. And in terms of having a particle accelerator, I mean it's much more souped up than the LHC. But the LHC you need massive magnets to, and it basically curves it round in a. I don't think anyone's built a particle accelerator that can sort of shoot out in very far in a straight line. There was a video, I never got around to watching, but there was a video about what would happen if you put your hand in the LHC, which I should probably watch so then I know the answer.
What do you think would happen if you put your hand in the LHC? It would hurt.
Yeah, probably.
Is this like a video on YouTube we can all go watch?
Yeah, I don't think they actually put the hand in the LHC. You're not allowed down there when it's on.
So So what you're saying is the Swiss are building a death ray gun.
No, because it goes round in a circle, so they're just death raying themselves.
But doesn't it nip into France every now and again?
I heard a hilarious story. I don't know if this is true, but that all the so there's 4 experiments in CERN, and I think they're all either in Switzerland or in France. They must all be in Switzerland, and I was told that the reason for that was that their health and safety regulations weren't as strict as France, but I have no idea if that's true.
Got any other questions?
I could talk about other space stuff. It doesn't have to be death rays.
You showed some really kind of cool bits of kit all around the world.
Yeah.
And slightly kind of off topic, but I'm just fascinated to know how, when you're doing a PhD, you're able as a PhD student to go and access these things and get the data from it.
Yeah, so there's sort of 2 sides to it. A lot of the data that I used in my PhD was from archives. So what tends to happen with these telescopes, like the Very Large Array and the VLT and all those other hilariously named telescopes, is that an astronomer will apply for time on the telescope to do their observations. They go, hey, look, this is a cool active galaxy, let me go and have a look for 5 hours or whatever. There's a time allocation committee who will say yes or no, and then either you go to the telescope or someone does your observations for you, and then you tend to have that exclusively for a year. And then after that year, anyone can go and access the archives. It's very, in that sense, it's very nice and open. So a lot of what I did was using the Very Large Array archives and downloading the data. And they may not have been pointing the telescope at the specific object that I wanted to look at, but it would have been in the field, so I could analyse the data. I did get to go, I went to the giant meter wave radio telescope in India, which is one of these interferometers. Went out there, went all the way to India for 9 hours of observations, which seemed a bit silly to me, but I wasn't going to complain. So I went and did that, and then most of them was archived. But even, as I say, even if you get the time on the telescope, you don't necessarily get to go there. So sometimes some observatories will just have a few astronomers that they employ full time to do all the observations, because then it means that you can schedule it. You can make much better use of the time. So, if I wanted to point the telescope over there and then over there, they take ages to move across. Whereas they might have also had people who wanted to point here, here, and here, and then they can decide the most logical way to do it. And it also depends on, for optical observations, it depends on, sometimes you need it to be really dark, and sometimes you can get away with having like the sky illuminated a bit by the moon and things like that. So the scheduling makes a lot more sense, I think, if you don't go and do it yourself. But
it's way cool fun though, just to be driving yourself.
Yeah, so some of them, and that's the other thing, it really depends. Some of them you go and you literally are controlling the telescope. Like someone will come and tell you what you're doing for a little bit, and then they'll leave you to it. So I've got a lot of friends who've gone to the Parkes radio telescope in Australia, which was the one in the film The Dish, if anyone's seen that. That one's cool because it kind of looks like they've got the dish, and then the control tower's like kind of the bit that it's sitting on, so you're like kind of sitting inside, I've been told. And the same, we're involved with a project at Portsmouth called the Dark Energy Survey, which uses a telescope in Chile, and quite a few of our PhD students have gone out there and they properly control it. When I went to India, we sort of sat there, we made our schedule, and then someone else controlled it, and I just ran around outside going, look, they're pointing at my things.
Taking selfies.
Yeah. But you do get to do a lot of cool travelling as an astronomer. I went to a summer school at the Very Large Array in New Mexico, and we all pretended we were in contact, which was kind of cool.
You had a slide that showed an electron swirling around or spiraling around the magnetic
field,
shooting off protons.
Shooting off photons, radio rays.
Sorry, photons. Yeah. Okay. Even so, that's energy. Where does that energy come from?
The electrons will. I think they slowly slow down as they're going on. I mean, they are hugely energetic. They are travelling, so close to the speed of light, and the radio photons are sort of the lowest energy ones. But they lose that as
Okay, so it's kind of just sloughing off bits of itself. And then...
Kind of, yeah.
Yeah, okay.
Not bits of the energy. It all gets very confusing when you're thinking about
Waves and particles.
waves
as
and
well,
particles. Yeah. Try not to think about it too much.
Cool.
You hinted earlier about some theories about things in the universe that might be slightly more immediate threats. Can you tell us a bit more about things that perhaps we should worry about more?
My biggest concern is asteroids. NASA and different space agencies do have dedicated telescopes and things to look out for big asteroids. I believe we are almost not quite due an asteroid the size of the one that wiped out the dinosaurs, if you look at how regularly these sort of things come around. And while we can look out for them, I mean, when was it? Was it a couple of years ago when that Russian meteor went over, and we didn't have any warning of that, and that was pretty big. I mean, that's not life destroying, but that was a pretty big thing to come out of the sky that no one had found before. And I think the danger is if one of them comes at us from the other side of the sun, because you won't see it because it will be obscured by the sun's glare. So you wouldn't necessarily know about it until it got quite close. But there are people working on ways to deflect them and all this kind of stuff. The other thing is if a star went supernova quite close to us. I don't know how close it would have to be, but if a massive star exploded, sort of the radiation from that could harm us. And then someone mentioned gamma ray bursts. Some people claimed that they found evidence that a gamma ray burst, so gamma ray bursts are, as they say, a huge burst of gamma rays that doesn't last for very long, but you see it sort of flashes in gamma rays that we think is to do with a supernova explosion. But because they are over so quickly, it's very hard to observe them. What you want to do is once you detect it in gamma rays, you want to point all your other telescopes at it to observe it and figure out, and you also want to go back to previous observations to see what was there before. Which is quite hard because we can't point telescopes at all parts of the sky at all times. So yeah, some people thought that there was evidence that a gamma ray burst had hit Earth before, and I think that would be pretty bad. I don't think any of this is actually going to happen to us. I think we're pretty safe.
What evidence would it leave behind in the geology? Or...
I think it left behind signatures in isotopes in sort of in the soil and might have been in trees or something. I can't remember.
Need to know how fast that
Okay. Anybody else got any?
Everyone should go buy Phil Plate's book and then we can read all about how the
Then we'll come back and discuss it.
Should have bought a copy.
Okay, well if that's everything, thank you very much, Jen. It's been in case you didn't notice when we had the slide up before, we're taking a break next month, just so that we can have a bit of a rest and have a think about what fascinating talks we're going to come up with for the rest of the year. If you've got any topics, this for example was a topic that came up in a couple of the very first meetings that we had, was somebody wanted something, quite a few people wanted something to do with cosmology. We do work on it, we do listen to you, we do meet people and we think, aha! Because Jen and I met in a field in the Isle of Wight, and I thought, aha!
We were at festival.
I was wandering through a field on the Isle of Wight,
and I was pointing at stars.
So if you've got any ideas of the sort of talks that you would like to hear, please give us some suggestions. You can contact us in all the usual ways. Facebook's normally a really good way of getting hold of us because I think it's the thing we check the most, isn't it? We're working, honest. So if you've got any ideas, please let us know what they are. We'll try, obviously we haven't got massive budgets, so if you're thinking Brian Cox or all sorts of other people, don't. But you know, within reason, we will try as hard as we can to try and get talks that you're interested in. So all we can do is thank Jen again, and thank all of you for coming out this evening. And most importantly, thank our lovely Boscanova staff for being here and serving us. So thank you.